Welcome to the Plasma Physics course of TPFL. In the past module, we have given a very short introduction to the plasma state. It's now time to become a bit more precise and give a rigorous definition of a plasma. In order to do that, as we will see, we need three definitions. The first one is the Debye length, second one is plasma frequency, and the third one, which is collision frequency. In the present module, we will focus on the Debye length. Plasma frequency and collision frequency will be the focus of the next module. By using these three concepts, we will see what is the parameter space of plasmas. So let's start. Let's start by giving the definition, the rigorous definition of a plasma. Plasma is an ionized gas. This is what we have pointed out during the first lecture. And now let me be more rigorous about what a plasma is. It's an ionized gas that is globally neutral and that displays collective effects. Two keywords. The first one is globally neutral. The second one, collective effects. What do they exactly mean? Well, to address this, we need to give three definitions. The first one is the one of the Debye length. The second one is the one of plasma frequency. And the third one is of collision frequency. Once we will have given these three definitions, we will be able to see where plasmas can be found in nature. In the present module, we will focus on the Debye length. And in the next one, we will look at plasma frequency and collision frequency. Okay, let's start by giving the definition of the Debye length. In order to do that, we will consider a simple scenario, the one of a plasma that is initially neutral. As a matter of fact, plasma come from the ionization of matter, and we expect in a plasma that the number of negative charges is equal to the number of positive charges. Now, in this plasma that is initially neutral, we insert a charged particle, a test charge. And what we study is the electrostatic potential that forms around this test charge. As we will see in finding out what is this electrostatic potential, a length will appear, which is the Debye length. So let's start by considering a plasma that is initially neutral, and therefore for which the electron density is equal to the ion density and is equal to N0. And we will assume that we are dealing with singly ionized ions. Therefore, that Z, the number of positive charges for ions, is equal to 1. We have therefore a system where there are a number of ions and of electrons which have the same density. And what we do in this initially neutral plasma is to introduce a charge, what we will call a test charge, with charge Qt. And we want to learn about the potential that will form around this test charge. And we want to learn about the potential that will form around this test charge. Well, to answer this question, what we have to do is to solve a Poisson equation, where the Laplacian square of phi is equal to the charge present in the system, that are given by the test charge, that is located at r equal to 0, plus the charges of the ions, that will depend on r, and the charges of the electrons. Well, in order to make some progress, we have to somehow state what is the ion and the electron density. For the ions, we say that they are heavy. When we introduce the test charge, they are so heavy that they don't move. So as a first approximation, we can assume that they constitute a fixed positive background with therefore an ion density that is constant and will be equal to n0. How about electrons? The electrons are light and therefore they move. We have to write down an equation of motion if we want to study where they will go. And this will be given by the electron mass times the derivative of the electron velocity. This will be equal to the forces acting on the electrons, which are given by the electric field, and the pressure. Now, pressure can actually be written in terms of temperature and density through the constant Boltzmann constant. Well, in order to simplify the notation, in plasma physics, we tend to agglomerate the Boltzmann constant inside the temperature, and therefore we will redefine Kb times the temperature simply as the temperature. Therefore, the temperature will actually be measured in terms of energy, joule or electron volts, for example. Now, to make some progress, this is already a fairly complicated equation. We make some hypotheses. The first one is that electrons are very light. They respond basically immediately to the insertion of these charged particles into plasma, which corresponds basically to take the limit of the electron mass to go to 0. Second hypothesis, we will assume that the electric field is given by minus the gradient of the electrostatic potential, and finally we will assume that electrons are isothermal, therefore that the electron temperature is about constant. Well, what is the consequence of this hypothesis? The left-hand side will be equal to 0. And this will be given by the electrostatic potential, the gradient of the electrostatic potential, the electric field. And then we will have the pressure term contribution, where we can assume that the electron temperature is constant. We can bring everything under the same grad symbols, therefore we will have that E gradient of phi minus Te, and we will write this grad Ne over Ne as the gradient of the logarithm of Ne. Well, this has to be equal to 0, which means that E phi minus Te log Ne has to be equal to constant, which means that the electron density will be given by N0 exponential of E phi over Te, where the constant has been determined by expecting that when there are no perturbation, no electric field, the electron density will be equal to the initial density, N0. Well, what does it mean if we insert this expression for the ion density and electron density into the original Poisson equation that we were looking at? We will have that Laplacian of phi will be equal to 1 over epsilon 0. We have to keep the test charge, and then we can place the expression for the ion density and the one for the electron density. Now, we can actually make an hypothesis that we will discuss later, that E phi over Te, this term here, is much less than 1. Basically, that the perturbations are small. If we do this hypothesis, we can expand this exponential at the first order the zeroth order will give us 1, and therefore positive and negative charges will cancel, and then we will have a term that is linear in phi. Basically what we will find is minus qt over epsilon 0 times Dirac delta of r plus e square and 0 epsilon 0 te. The term that is comes from the Taylor expansion of this term here times phi. This will be therefore equal to minus qt Dirac delta epsilon 0. Well, if you look at this term here, you find that this is the inverse of a length square. We call this length the Debye length, the electron Debye length, and therefore this equation becomes 1 over lambda dE square phi, where the Debye length is equal to the square root of epsilon 0 dE e square and 0. This is the electron Debye length, one of the most important quantities in plasma physics. So we have reduced the problem of finding the electrostatic potential around a test particle to the solution of the following equation, where I have brought on the left-hand side all the terms in phi. This equation can be solved. I spare you all the details. Well, let me just mention that one has to work in spherical coordinates, but without going to the details, let me just give the solution of this equation that tells you that the electrostatic potential will depend on the distance from the test particle r as 1 over 4 pi epsilon 0 qt over r times the exponential of minus r divided by the Debye length. And here we notice something interesting, that the electrostatic potential that we would expect for a charge in a vacuum, 1 over 4 pi epsilon 0 qt over r, is modified by the presence of the plasma, that is this term here, by this exponential. So how does this electrostatic potential looks like if we try to draw it? Well, first of all, let's plot the standard Coulomb potential 1 over 4 pi epsilon 0 qt over r. It will have a shape like this one. And if we plot the potential that we obtain in a plasma, we observe that there is an exponential factor here whose argument is always negative, which will provide a screening. Now, where this screening will become important is when we are at distance r of the order of the Debye length. This is when the deviation from the Coulomb potential will become important. So what is the effect of the plasma is actually to screen the potential that a charged particle would have in vacuum. What we have here, which is the case of a plasma, is a screened potential that we will call the Debye screened potential. So let me make a few observations. The first one is that in order to describe the plasma, we have used concepts like density. If you want, we have forgot about the fact that charged particles in a plasma are discrete. We have used a statistical approach that makes sense only if inside the volume given by lambda dE cube there is a high number of electrons or ions. In other terms, if n, the plasma density, times the lambda Debye cube, this is what we will call n capital D. number of charged particles in a Debye cube is much greater than 1. Otherwise, if this is not respected, then the treatment that has led to say that the Coulomb potential is screened with respect to a vacuum is not valid anymore. We would have to look at the single, the discrete nature of the particles. Second observation, if we want to give an estimate of the Debye length, well, this will depend basically on temperature and density, and will be given by 6.9 square root of Te over n0 centimeter. If you express the temperature, the electron temperature in Kelvin, and the density in terms of particle per centimeter cube, or you can also express lambda Debye as 7 times 10 square root of Te over n0 meters. But in this case you have to express the electron temperature in electron volt and the density in meters, particles in meter cube. So what are the conclusions? What have we learned by doing this exercise? Well, the first conclusion that we can draw is that in order to have deviation from neutrality, or to be more precise from quasi-neutrality, which is the initial state of the system, well, we need to have that the electron density, which is given by n0 exponential E phi Te, becomes different than n0. And this can occur only for distances that are smaller than the Debye length. In fact, at distances that are larger than the Debye length, the perturb potential will tend to 0, and therefore n E will tend to be equal to n0. Now let me point out that this procedure requires to have nd much larger than 1. And there is a second conclusion that we can draw, which is quite important. So let's go back to the hypothesis that we have done in the previous slide, where we have assumed that E phi over Te was much smaller than 1. Well, what does it make sense? After all, phi goes to infinity for r going to 0. Well, but actually it does not make much sense physically to go to r equal to 0. There is a minimal distance until up to which looking at this equation makes sense. In fact, what we have to do is to evaluate the electrostatic potential at the minimal distance that makes sense to look at, where therefore the Debye screening will not have intervened yet, and this minimal distance will be given by the typical distance between particles in a plasma, which will be given by the cubic root of 1 over n0. Therefore, if we want to evaluate E phi over Te, we can write this as use this expression for E phi with the minimal distance given by this expression, and we can multiply and divide by n 0 to 2/3. We will get therefore at the numerator n0, and now we can recognize a quantity that is the Debye length here. In fact, this will be given by 1 over 4 pi, 1 over the Debye length square, 1 over n0 to the 2/3. And here what is? This can be put in relation with nd, and is equal to 1 over 4 pi nd to the 2/3. And this is okay because we have already required that nd is much bigger than 1. therefore this will be much smaller than 1, as we've asked. So where is the conclusion? Well, actually, we can draw one consequence from what we have just written here. And this will be much smaller than 1, because we have already required that nd is much larger than 1. Well, actually, by looking at this, we can notice one thing, is that one-to-one interaction between particles is weak if I over Te is much smaller than 1, which means for nd much larger than 1. In fact, if nd is much larger than 1, then the electrostatic potential that acts between two charged particles will be much smaller than the electron temperature, and therefore the one-to-one interaction between particles will be weak. In the present module, we have started to introduce the fundamental concepts that are required in order to give a precise, rigorous definition of a plasma. In particular, we have introduced the concept of the Debye length. We have seen that quasi-neutrality of a plasma is a concept that makes sense at distances that are beyond the Debye length. And second thing, we have pointed out that one-to-one particle interactions are weak if the number of particles in a Debye cube nd is much larger than 1. In the next module, we will look at the definition of plasma frequency and collision frequency, and through this we will fully understand the rigorous definition of a plasma that we have given here in this module, and we will look at what is the typical parameter space of plasmas